Hi everybody. So this tutorial follows up from your Ramps and Work lab. We're going to talk about the key concepts from that and also relate it to simple machines. So you look at the title above here. And if you didn't know already, when you use a ramp, you are using a machine. It's a simple machine because there's just one part. There's no moving parts to it. There are other simple machines. You may have learned them in middle school or elementary school. The inclined plane, a pulley, lever, wheel and axle, wedges, and screws. Okay, so they all serve the same purpose. And for most people, they get the purpose wrong. Most people think the purpose of a machine is reduce the amount of work done when doing a chore, a task, or something like that. And what you saw in your lab is actually just the opposite, or at best, there's no advantage at work. Okay, so what is the purpose of a machine? And how you make more machine, and that's not the best term really, is all about increasing the length over which you do a work. In other words, more ramp means a longer ramp. More pulley means more advantage from a pulley comes from more pulleys. On a wheel and axle, it's a bigger radius. So it's what we want to look at is what advantage do we get? And the advantage that you get that was clear from the lab is it reduces the effort force, okay? It just makes it easier to do it, okay? And it's easier to do work. That does not mean less work. It's less force. And that makes sense because the longer the lamp you use, the smaller the angle it's going to make with the vertical, and so the parallel component of the force is going to be less because it goes by the sine of the angle. So we'll show that in a minute. In terms of work, under ideal conditions, okay, this is the best you can hope for. In other words, there's no friction, no resistive forces. The length of the ramp does not affect the amount of work done. In your lab, it should have been pretty clear as you rolled the car up the ramp, the amount of work done for a steep ramp or a shallow ramp was essentially the same. That is not the case when there is significant friction. So we'll talk about that in a minute. But before we do that, I want to show you theoretically why it should not matter for the angle in terms of the work done, because this turns out to be actually really important when we start talking about energy. Okay, so I'll say it again, it's very, very important. The work done to go from one level to another is independent of the ramp length, or more generally independent of the path you take. The ramp could be curvy, it could be stepwise, like literally as stairs. It doesn't matter. In fact, that was the assumption we made for the power lab, is when you're up the stairs, the forward motion in the stairs did not affect your work. So let's look at two situations here. I have an incline, right, of a height h and a length d. We have two ways of getting to the top of the incline. We can go straight up, or we can go up along the ramp. So along the ramp is a greater distance. We want to calculate the amount of work done in each case from a theoretical standpoint. So let's take the most direct route to lift it straight up. So to lift it straight up, we ask ourselves, what force do we have to exert or overcome? Well, that's gravity, mg. So the work done is simply, right, I'm just going to put a generic f of g times an h, and that equals mgh, right? That's pretty simple. This equation, we're going to see a lot over the next few weeks. So you don't have to worry about it so much right now. This is just an illustration, but you will recognize it again and again. Okay, so let me rewrite that. Now let's take the other approach. We're going to go along the ramp. So in this case, the work is what force? Well, it's the FG parallel. And what's our relevant distance? D. So how do we calculate FG parallel? Well, hopefully I've forgotten that's just mg sine theta multiplied by d. Okay, does this look like this? Well, there's m and g in common, but h doesn't look like sine theta d. However, if we look at the triangle we have here, if this is theta, we can say the sine of that angle is opposite over hypotenuse, h over d. So we can do a little algebra, and we can see that h equals d sine theta. And sure enough, if this is h and here is d sine theta, they're the same thing. That tells us you must do the same work going up the incline. What matters ultimately, and this is again going to be really important later on, is if you want to calculate work to lift something up, doesn't matter how you get it to the different height, what matters is the height and the weight. That's the easiest way to calculate it. This is a valid equation, but you could just as well calculate it using this. And that doesn't matter whether the ramp goes up like that, or like I said earlier, it's a staircase. Ultimately, the amount of work done is equal to the height that you're going to multiply by the weight. And again, that's only for the criteria where there is no resistive forces. And it'll often be the situation we're interested in working with. Okay, so to finish up, under real conditions, okay, the previous case was ideal. Real conditions means there's resistive forces. Increasing length increases the amount of work done. And that's counterintuitive. Most people, again, think the purpose machine is reduce work. In fact, we're seeing it increases work. And if it increases work, that means more energy must be consumed the longer the ramp is. So if we talk about the long and winding roads that go up mountains or paths or to different flights in a home or building, you're doing it at the expense of energy, but that's all right. We do it because it's less effort. It's easier to do, and that's what ultimately matters. So in summary, one always does more work when using a machine, but it makes it much easier. Okay, and that's not only true of ramps, it's true of all those simple machines above. If you want to make it more easy, and this is something else you can do, you make it longer, okay? So easier, easier again is a force, not work, translates to longer distances. That's the, if you will, sacrifice. So on a pulley, if you've ever been in the backstage where you have to open curtains or lift up very heavy props, you look at the pulley system you have there, you might lift it, let's say 10 feet up, and you might have pulled 30 feet of rope or 40 feet of rope. That's all right because it makes it a lot easier.